everyone, this is the first of a two-part lecture on plate tectonics and plate boundaries. I want to start by reviewing the layers of the Earth. We have defined, of course, the crust, mantle, and core. The boundary that separates the crust from the mantle is shown here. I'm tracing it in red. We call that the MOHO, or Mohorovičić discontinuity. But when we're talking about plate tectonics, what's really important to think about is not just the crust, but the crust plus the uppermost rigid part of the mantle. Together, those make up the lithosphere. And the tectonic plates of planet Earth are composed of lithosphere. Again, the crust plus the uppermost rigid mantle. Lithospheric tectonic plates ride on top of a warmer and weaker part of the mantle, which we call the asthenosphere. So it's down here shown in orange. The asthenosphere is warmer, it's weaker, and it is capable of behaving plastically, which means that over large timescales and distances, it can flow, much like silly putty would. If you rolled up a ball of silly putty and let it sit on your desk for long enough, it would turn into a pancake. Again, I want to point out that the mantle is solid. Even though we draw the asthenosphere in these warm colors and we say that it's capable of flowing, it is not liquid. This is a common mistake that new geology students make. The asthenosphere is still solid mantle, but again, much warmer, so therefore weaker and capable of deforming plastically, even capable of flowing over long time scales and spatial scales. Okay, so we've got these rigid outermost lithospheric plates that are capable of moving on top of the plastically deforming asthenosphere. We can see in the picture here, you could divide the lithosphere into two fundamental different parts. So over here, what I'm tracing in yellow is very thin lithosphere, and that underlies the world's oceans, where the crust is also very thin. Underneath the continents, the crust is much thicker, and the lithosphere also is thicker, and you can see that in this diagram here. We talked a lot about seafloor spreading, so I thought I would use this image here to remind you guys about seafloor spreading. At mid-ocean ridges, you have two oceanic lithospheric plates that are pulling apart from one another. So this plate is moving to the left and this plate is moving to the right. That causes the asthenospheric mantle to partially melt and for that magma to rise up and to plug this gap here at the mid-ocean ridge. Some of it spills over and makes brand new basalt of the oceanic crust. But nearly as soon as that basalt is made, it is translated to the sides of the mid-ocean ridge and is pulled apart. That basalt, of course, solidifies and becomes the oceanic crust. So what I'm dashing in here in red is the basaltic crust of the oceans. And that doesn't change thickness as you move away from the mid-ocean ridge. However, the lithospheric mantle, which is also being produced through this process of melting and crystallization at mid-ocean ridges, or spreading centers if you want to think of them like that, the lithospheric mantle does become increasingly thicker and cooler as you move away from the mid-ocean ridges. So far away from the ridge, it's thick and cool. Close to the ridge, it's quite a bit warmer and thinner. So yeah, I want to make sure you see that the oceanic crust stays the same, but the lithospheric mantle becomes thicker, denser, cooler. And this is important because the ever thickening and densifying lithospheric mantle can eventually end up acting as a ballast, which will pull the entire tectonic plate down and press it into the asthenosphere, forcing the asthenosphere to flow out of the way. As I've said before, oceanic lithosphere is on average much thinner than continental lithosphere, and that's in part because oceanic crust itself is very thin. So here's our oceanic crust. You can see that it's very thin. On average, oceanic crust is 75 kilometers thick. On the left, you can see continental crust is quite a bit thicker. So it's probably on average about 25 kilometers thick, but can be anywhere from very, very thin, as it is over here, to say very thick as it might be under Mount Everest. Something like that, 7 to 75 kilometers thick. So the continental crust is thicker but very variable. You can think about continental lithosphere as being made of a thick oak block, which was this thing here, plus a non-dense but very thick cork sitting on top of it. For that reason, the continental lithosphere tends to bob above the sea level. In contrast, the oceanic lithosphere also has this oak block here. That's the lithospheric mantle part, although it's much thinner. And on top of it, a denser, thinner kind of pine crust, if you will. And so you can see here that the oceanic lithosphere sits lower relative to the continental lithosphere. And for that reason, it is typically covered in seawater on planet Earth. So those are what lithospheric plates are made of. These plates can be made of just oceanic lithosphere, just continental lithosphere, or a combination of the two. The edges of lithospheric plates are called plate boundaries. So as you know, our planet isn't just one solid, unmoving, unchanging sphere of lithosphere. Rather, the exterior of our planet is broken into many different lithospheric plates that can move relative to one another. And where they bump into each other or slide past each other, or in the case of mid-ocean ridges, pull apart from each other, are called plate boundaries. So you've been working with a map similar to what's shown here in your first problem set for our class. And you can see it's a map of the world, but broken into different kinds of lithospheric plates. Again, notice that not every continental margin coincides with the edge of a lithospheric plate. Where the edge of a continent is in the middle of a lithospheric plate, like it is here in the eastern United States. So here's Florida, Georgia, South Carolina, North Carolina, etc. There's the edge of North America. You can see that you are smack dab in the middle of the North American plate. This is not an active plate boundary. So the eastern side of North American continent would be considered a passive margin. In contrast, let's look at the western edge of South America. So down here is Chile, Peru, Ecuador, etc. going north. Notice that the edge of this continental plate coincides with the edge of the South American plate. This would be considered then an active margin, where the edge of the continental lithosphere coincides with the edge of the lithospheric plate. In contrast, the eastern part of South America would be a passive margin. Let's look at Australia. All of the edges of Australia are inside the plate, so all of Australia has passive margins. Okay, Eastern Africa, passive margin. Okay, Northern India, active margin. You'll notice that if we look at that same map we were just investigating and we compare it to a map of global earthquake locations, you can see that earthquakes occur in very distinct belts and that those belts more or less define tectonic plate boundaries. A great example of this is the Philippine plate. So the Philippine plate is like a subplate that's in the middle of the Pacific Ocean, and you can see that I'm sketching it out here on the plate tectonic map, and you can see it very clearly delineated up here in the earthquake map. That's pretty cool. So where the Earth's tectonic plates are moving against one another in some way, earthquakes are being generated. So earthquakes delineate these plate boundaries. Next, I want to discuss the different types of plate boundaries. We will start this discussion in this lecture, and I will continue it in lecture plate boundaries part 2. let's start with mid-ocean ridges. These develop in what we call divergent plate boundaries. To diverge means to move away from one another. So in divergent plate boundaries, two lithospheric plates are moving away from each other, they're pulling apart. That is typical of what happens in the middle of the world's oceans, where two lithospheric oceanic plates are pulling apart at seafloor spreading centers. And when that happens, they create these mid-ocean ridges, and new basaltic crust of the seafloor is made, and new lithosphere here is made, and then it cools, becomes dense, and moves away from the spreading center. I've put a note here. I'm not going to go to this animation right now, but your textbook has a really excellent animation that is linked in Canvas, and I highly recommend that you go and watch that animation. It does a great job of explaining divergent plate boundaries. We could summarize that animation by looking at a figure such as this one. This is also from your text. And in this figure, we are stepping through time from top to bottom. So at the top, we've got a relatively young ocean floor. So not very much basalt has been created. It's a pretty narrow ocean basin. You can see that it is bisected by a mid-ocean ridge, which is right here. Sometimes that gets abbreviated MOR, if you ever see that abbreviation. It's a mid-ocean ridge. So here, notice that we're only showing the crust, so you're not seeing the lithospheric part of the tectonic plate here. And that's just for simplicity's sake. So during the development of mid-ocean ridges and new seafloor at divergent plate boundaries, melted mantle is rising up, creating this red slot here that crystallizes and turns into brand new basalt of the seafloor, and that basalt gets moved to the side of either side of the mid-ocean ridge and pulled apart. Step forward in time, and you can see that the seafloor has become quite a bit wider. And step forward in time again, and it's become wider still. And over this time, remember that the magnetic polarity of Earth's magnetic field is probably reversing, such that here you might get basalt that is crystallizing in a normal magnetic polarity event, but through time you might have basalt, so this yellow would be that earlier crystallized basalt that moved away during a normal event, and now we're in a reverse period and we're making this basalt. Step forward through time again, and now we've got our really old yellow normal basalt out here. We've got our reverse basalt that we made in part B, and now we're back to a normal time, and now we've got this new crust that's being created. So our ocean is ever widening, and we're creating this bar stripe pattern of magnetic anomalies on the seafloor, shown here as yellow, green, yellow. A mid-ocean ridge is much shallower than the deeper abyssal plains next to it. That's because as the two plates pull apart, it actually forms a chain-like mountain, a long mountain chain that bisects the world's oceans. These ridges can be offset along their length by transform faults. And so that's what you're seeing here in all of these little features that offset the mid-ocean ridge. And that's because our Earth is a sphere. And so if you try to pull a sphere apart, you can't just create one long gash. You could do that if it was like a flat piece of paper, but on a sphere, that pull apart has to be accommodated by these transform fault systems. And some of them are quite long, like you're seeing here. A magma chamber exists beneath the ridge axis. Molten rock, which we'll discuss in the next segment of this class, flows out onto the seafloor and produces something called pillow basalt. So this is just basalt that has an unusual form because it's developing or crystallizing very rapidly as it pours out into cold seawater. Some basalt actually gets injected as like these dikes. That's those are these kind of subparallel features like here. So you can think about some of this molten material kind of squirting up into fractures in the pre-existing oceanic crust and filling it that way. At depth, you get the development of something called gabbro. Gabbro is compositionally identical to basalt, but we give it a different name because it crystallizes beneath the surface of the earth. Two slides here, and you can see that the the basaltic crust of the oceans is highly broken up by these fractures, some of which get filled with basalt, but it's very rich in fractures. Well, what happens? This is a really cool picture of a pillow basalt that was taken with a rover from the bottom of the seafloor. And you can see these kind of lumpy, bumpy forms that are developing in the basalt. And so these are what we call pillows. And it's very distinctive of basalt that forms on the seafloor. And so occasionally you'll see pillow basalts exposed in mountains or cliffs somewhere today on the continents. And when you see that, you can feel confident that you're looking at basalts that would have formed deep within an ocean, or deep on the floor of an ocean somewhere. Just rewind is that another really cool feature of mid-ocean ridges are something called black smokers. So water fills in those fractures, then becomes heated by the magma at the mid-ocean ridge. And so now you've got hot seawater, which is being circulated through the oceanic crust via these fractures. It's capable of dissolving materials in the crust. And so now imagine that you have super hot seawater that has a whole bunch of dissolved metals and ions in it. When that seawater gets recirculated to the surface of the seafloor, where it will interact with cold water of the ocean, all of a sudden it dumps out all of the dissolved ions and metals it was carrying, and the result is a plume of black smoke here called black smokers. So the smoke is essentially all of the stuff that got dissolved into the hot seawater that was inside the oceanic crust once it was kind of blown back out along these fractures near the mid-ocean ridge. So these are very hot, and it turns out that there are some organisms that are considered chemosynthetic that live off of the ions and metals that are extruded here at these black smokers. I'm going to leave you with this picture here about a map of the seafloor. So I've told you that over time, thanks to seafloor spreadings, the oceans are getting wider and wider. The Atlantic Ocean is constantly pulling apart, spreading apart. But if you look at this map, you'll notice that there is no seafloor anywhere on planet Earth that's much older than, somewhere in here. Notice that there are hardly any colors that get cooler than blue. So the question is, why? Why is it that we don't preserve any seafloor that is older than about 180 million years old? And to answer that question, you need to think about what is happening on the Earth. Can the Earth's oceans become infinitely wide? So that's my question to you. We'll pick up that question in the next part.